if you come up with a hypothesis, let alone it gets elevated to a theory, you need to be able to predict how things are going to behave. Okay? And Newton's laws of motion do that quite well for objects on Earth and galaxies. So in order to, before we get into Newton's laws of motion, let's talk about motion just a little bit. Now, there are no numbers that you need to crunch in this class, but we need to be able to kind of talk about things like speed. Okay, so you're driving down the road. How do you say how fast you're going? Basically, you take how far you went divided by the time it took you to get there. Okay, distance over time. Okay, to say how fast you're going. That's speed. Now, there is a slight difference between speed and velocity, even though we kind of just say speed, velocity is the same thing. The thing about velocity is not only does it say, distance over time, but velocity also says what direction. And it's what we call a vector instead of a scalar. So like this says, what we can do then with velocity to show direction, it's kind of, if you're a visual person, it's kind of nice in physics. They basically just use an arrow. So for instance, we would say, we could show velocity by doing this. Okay, that's kind of what, northeast-ish. Okay, and this is northeast-ish, twice as fast because it's a longer arrow. Okay, so that's how they do that. In fact, what you can do is if you draw them to scale, and you can actually kind of move them around and connect them up and understand what we call the resultant vector is. Okay, because sometimes there's more than one velocity or force going on. Okay, so velocity adds direction to speed. Now, acceleration by definition is a change in velocity. Acceleration is a change in velocity. Most people, if you ask, or kids even, it's like, what is acceleration? I'm like, well, it's when my mom's driving down and there's like a yellow light and she hits the accelerator. That's acceleration, okay? She goes from a particular speed to a faster speed, okay? So acceleration is a change in speed as far as he's concerned. But acceleration can also be a change in direction, okay, since it's a change in velocity, and velocity also includes direction. So these are all accelerations. Going straight, starting at 30 kilometers per hour and ending at 60 kilometers per hour. The acceleration is 60 minus 30, or 30 kilometers per hour. That was the acceleration. This is also acceleration. You maintain the whole 60 kilometers per hour, but you change your direction. That's also acceleration. That's important because I want you to kind of think of, in here we've been talking about how the planets, orbit the sun. We are continually changing our velocity. We are continually accelerating. Anything that's going in a circle is accelerating. I don't care if it's keeping the same speed, but it's changing direction. Okay, it's changing its velocity. The other type of acceleration sometimes we don't think of as much because we think of an accelerator on our car, but if you slow down, you're also changing your velocity. We call it deceleration. It's like negative acceleration. So that's what this other one's showing you. Going from 60 kilometers per hour, slowing down to 30 kilometers per hour, and then finally stopping. This type of acceleration. This is important because here in a minute, I'm going to show you how Newton's laws of motion has an acceleration term in it. And it says nothing can accelerate. Okay, I'll put it this way. If something's accelerating, whether it's speeding up, if it's changing its direction, or if it's slowing down, if it's accelerating, something is causing that acceleration. Specifically, some force is causing that acceleration to occur. Okay, that's Newton's second law. Speaking of Newton, so go ahead, skip ahead a few slides if you want to. I went ahead and I'm not sure why I have them in the order I do, but you need to find this slide. And there's 3 slides basically I'm going to go ahead and knock out right now. Okay, so Newton's first law of motion. There are 3, okay, plus the law of gravitation, plus I'm sure he did the whole calculus thing, but 3 laws of motion, okay. The first one says that an object will maintain what it's doing, okay, unless acted upon by an outside force. And it makes sense. These make sense. Okay, Newton said, for instance, okay, an object moves at a constant velocity. Now, the velocity of that blue pen is 0. So actually, we can apply Newton's first law to that. That pen is going to stay there unless acted upon by an outside force. Put another way, and this doesn't work very good on Earth because we have friction and gravity, but if you're in outer space where you don't have any friction, or I've heard it put recently that in outer space you still have gravity because there's some star, you know, you're not in a universe of all your own. But let's just say you're basically nothing around you, no air molecules to slow you down. If you start in motion according to Newton's first law, it's basically going to go forever. Kind of reminds me of that 2001, and the tablet falls on that, and the monkeys are all going around. Do you remember that one? Am I dreaming how that movie goes? Okay, something like that. So something in motion will stay in motion. Sometimes it's called the law of inertia. Okay. Inertia. Inertia just basically says objects, because of their mass, they will maintain what they're doing, how they're doing it. Okay, so inertia actually is related to mass. Here in a minute I'm going to talk about momentum, and momentum is very kind of similar to inertia. They're both related. Makes sense. These are Newton's make sense laws. So let's go on to the second one there. Now this is where the acceleration, this is kind of why we needed to talk about acceleration a minute ago. So acceleration is something speeding up, slowing down, and or all of the above, changing its direction. It can keep going the same speed but change its direction. That's acceleration. So this is where I said no acceleration occurs without a force making it happen. Specifically, I think this is kind of cool mathematically if you think about it. The force is equal to mass times acceleration. F is equal to ma. Sometimes on my Unit 2 exams I've said, describe Newton's laws of motion. If you just put F is equal to ma for his second law, kudos, okay? It relates basically the force, or I think a force is a push, okay, the resulting acceleration and how it's related to the mass that the force is being applied to. So the example here, I think this is from your textbook, okay? If you want that ball to go from 0 kilometers or 0 meters per second to very fast, okay, that pitcher is going to apply a force to that ball. And it's going to accelerate from 0 to very fast. All right, his third law, okay, this is one where I always think of like, this is one where you tell your kids, don't fight, because if you hit your sister, she's going to hit you back. Or maybe you encourage the sister to hit the brother back. Okay? So for every action, there is an equal but opposite reaction. Okay? And the example given here is the thrust that's created by a chemical reaction by the rocket. Okay? So there is a thrust downward by the chemicals, and there it results in an equal but opposite thrust upward to propel your spacecraft. So you got it going like this. So Newton's third law of motion. So, okay, so now go back to this slide. So one of the things, and you may or may not know this, but if you were to climb a building, okay, and drop something and be able to clock how fast it's going as it drops, it's going to go faster and faster and faster. What is that? That's acceleration. And what's it caused by? Basically, gravity is doing that. The mass of this object and the mass of the planet Earth are interacting. Okay, it's the mutual attraction. I know the Earth's not moving up to the pen, okay, but the pen is moving down to the center of the Earth. So here we go. Almost looks like that guy is like I hate to say it, but like, just now when I saw it, it looks like he's like urinating over the side, but he is not. He is dropping a ball, okay? Now some of you may have learned this acceleration is 9.8 meters per second for each second it falls, and that's cool. If you round 9.8 up to one significant figure, you get 10. So your book goes with 10 meters per second. That's how it goes faster for every second it falls. So that's why, kind of handily, this little figure says it starts at 0. Velocity is 0 at time 0. In 1 second, it now is falling 10 meters per second. You let another second lapse, and now it's falling 10 plus 10 or 20 meters per second. Okay? If the building were taller and it was able to fall another second, the velocity would be approximately 20 plus 10 or 30 meters per second. That's kind of how this works. It goes faster and faster and faster and faster and faster and faster. Yeah. If it's accelerating, according to Newton's second law, some force needs to be causing that acceleration. And like I said, it's the force of gravity. We're going to call that F sub g, I think, here in a minute, force of gravity. So here's one that sometimes even I struggle with. No, it's kind of like if you were to drop two objects, and let's make them bowling balls. Let's make them kind of the same volume, but let's make one like a bowling ball that I might use, and let's make lighter, and then another one that's a bowling ball that a pro might use, so it's heavier. But they have the same physical characteristics. Usually you would think the heavier one would go faster and faster and faster. It would accelerate so that each moment in time it actually would fall like that, right? That's not the case. Okay, the acceleration due to gravity is independent of the mass. They both accelerate at the same rate. That is true. Now, the deal is if you take a feather, okay, with a certain mass and a bowling ball, okay, the bowling ball is going to hit the ground first. The thing about the feather is that it's going to catch the air molecules. Aerodynamics set in. One of the things astronauts did when they landed on the moon was to take a hammer and to take a feather and to drop them at the same time. The thing on the moon versus on Earth is there's really no air. There's no air particles to make aerodynamics an issue. So actually, and there's a video, I don't think I pulled in, but there's a video out there that shows them dropping at the same time. Accelerating at the same rate. I think that's cool. Oops. So gravity, and I have an equation kind of to show you what is this gravity, okay? When we drop something, it's this is mutually attracted to the Earth, and the Earth is mutually attracted to the pen. All right. So remember Newton's first law, I said, was kind of what we call the law of inertia. Inertia and momentum are kind of similar, okay? So, what is momentum? Momentum, though, only objects that are in motion have momentum. It's kind of like if you get home and you sit down and you're like, oh, I lost my mo. You might be saying, I lost my momentum to do anything. I have lost my momentum. Only objects in motion have momentum. They have momentum. It's like a little math problem. You can basically say how fast they're going, their velocity, so it also is a vector quantity, how fast they're going and how much mass they have. So this whole momentum thing, this is why, like if you have a Mack truck driving 35 miles per hour down the road versus a versus a bicycle, something lighter. So a Mack truck versus a bicycle, both going 35 miles per hour, okay? The truck has a heck of a lot more momentum than the bicycle does. I would rather get hit by the bicycle than the truck, okay? So mass is a player. But momentum is kind of similar to inertia. So We're going to talk here in a minute about angular momentum. So momentum is associated with the mass of an object and how fast it's moving. The faster it's moving, the more momentum it has. The more massive it is, the more momentum it has. Okay? Momentum, though, like Newton's first law, momentum says there's a conservation of momentum, and momentum will continue. It's kind of like the throwing something in outer space. Okay? You're just going to keep that momentum. You're going to keep going unless something acts upon, force acts upon you. Okay? So as we kind of talk about, I've thrown the word force out there, nudge, okay? As you know, it's quite possible that more than one force can be acting at one time. So for instance, like if I roll this pen down, okay, it eventually stops. Two forces we have right off the bat are this force, the force of friction, right? And this force, the force of gravity. I should put this force, the force of gravity, okay? So two forces working at the same time, which makes physics problems a bear. Okay, but we're not going to do any physics problems. Okay, but just kind of keep that in mind. Okay, and this is kind of what I said a little bit ago. As you drop something from a rooftop, it doesn't go a constant speed. It basically is going to go faster and faster and faster and faster. Now, I will say there's this thing called terminal velocity, which basically means its speed is going to top out. But again, terminal velocity only exists because Earth has an atmosphere that is creating some sort of cushion around that object. Yeah,
Drag.
so, drag, excuse me, thank you. If there were no little gas particles, there'd be no drag, and terminal velocity would not be an issue. All right, so mass versus weight. I even kind of throw them around interchangeably, but they are different. So here's the deal. The mass of an object is the amount of stuff there is in that object. Specifically, quite frankly, it's kind of the amount of atoms that are there. And we can actually talk about a unit of mass is kilograms. Weight, on the other hand, weight, on the other hand, basically takes the mass, the kilograms, and it adds gravity to it. So here's the deal. If I have an object that has a certain mass here, and I relocate it to the moon, it's going to have the same mass. Okay. Weight, though, no. Okay. I take an object, I calculate its weight here. Okay. Actually, weight is best as a type of force and kind of what we call newtons. So it has a certain weight here because of gravity, mass, the masses of the object and the Earth interacting. If I take that object to the moon's a lot less massive, and it's going to have less weight. It's going to weigh less. So in order to calculate that little w is the variable for weight. In order to calculate w, a weight, what you got to do is take the mass times the acceleration due to gravity for wherever it is, Earth, Moon. So for us, it would be that 10 meters per second, or 10 meters per second squared. So the mass of an object is constant, but the weight will vary depending upon where you're taking the weight. Okay, so for instance, if we look at the moon, all things considered, and it's not just the mass of the planet you're standing on. When we talk about black holes, okay, it's also your proximity to the center of mass. The problem with a black hole, quite frankly, is you are so close to the center of mass. Here on Earth, we're like, oh, we have a fighting chance. The center of mass is, like, I don't know, a ways down there, where the dinosaurs are, okay? So we would weigh 1/6 that we do on Earth on the moon, but our mass would be the same. So here we have, this is a classic kind of from left to right. These are different scenarios of a person in an elevator trying to weigh himself. Okay? So from left to right. So the thing about it is, if the elevator is stationary, okay, this person weighs 140 pounds. Okay, if it starts accelerating upwards, okay, notice that his weight goes up, because weight is basically taking the Earth's acceleration, 10 meters per second squared. Okay. Well, if the elevator's also accelerating, now he's got extra acceleration, so he's going to weigh extra. Okay. Here, it's going to accelerate downwards. Okay. And actually now, as it accelerates downwards, he's going to weigh less. And this is just kind of intuitively. Okay. His acceleration now is less. Okay. Now here, it's going to. The cable's going to break. I hope he's not very far from that bottom. That's kind of a scary deal. Okay, and so he is free falling. So basically, the scale that he was standing on is not bearing his weight. And so his weight just basically, he can't use the scale to weigh himself anymore. It's free fall. Speaking of free fall, okay. So if you've ever watched the folks in the International Space Station, how they float around, doesn't that look like fun? The logistics, well, if you haven't, you'll have to watch some of their videos, because they are quite socially into things. They have a great Twitter feed and post videos of what they do. Life is difficult when you're in the International Space Station. The whole peeing thing, and I don't know, it's very hard. But the deal about objects that orbit the Earth, okay, they are actually what we call in constant free fall. So here's how this goes. Picture, this is the deal, this is kind of weird, but here we have a guy who climbed a ladder, right? And here is the plank that person stepped off of. Okay? He stepped off going a certain speed and just fell down. Whew, that's not good. Okay? He stepped off going a little bit faster, and notice where he fell. Okay? He fell a little bit farther from the Earth. Why? Because he kind of had a running start. Okay? Now picture him getting smart and adding a little bit of propulsion. Okay? So that gives him a lot of stepping off power. So he steps off, he's still falling, free falling. So he's still falling, but notice that he misses the Earth. He's got this trajectory going and this trajectory going. This would be gravity, okay? And this actually is, initially it was his thrust, but according to Newton's first law, once he gets in motion, okay, he can stay in motion, okay, unless some force is acting upon him. Actually, there is a force acting upon him. It's gravity. It kind of evens him out.
Could that even happen?
Yep. He's inserted into orbit right there. Have you ever heard the term inserted into orbit?
You're just going to need like a big old oxygen tank in a space.
Oh, wait a minute. Maybe not, Nellie. I'm like, really? Could you? No. I don't know if anybody's really done this. But this is kind of the idea when they put like inanimate objects in orbit about the Earth.
Yeah, I don't think a person can do that because
Yeah.
eventually they'd kind of be stuck there, first of all.
Yeah,
Unless,
I don't think they have.
Well, if like Greta jumped out of that thing.
how would you get out?
Yeah,
Okay,
the
so
Red Bull.
Yeah,
jump?
that's all I can remember from it was Red Bull.
So say a person does attempt this and they succeed and they get in this orbit with the Earth. How do they get themselves out of the orbit?
Well, that won't matter because they did it.
Yeah, until they die.
Well, have you ever heard
from
of
asphyxiation.
Yeah, but have you ever heard of their orbits decay? Like when we do insert like a satellite in orbit, eventually they fall to Earth. Okay, so like the molecules in Earth's atmosphere, there aren't much up there, but they kind of give a little bit of friction, so they kind of lose a little bit of energy, and so they eventually fall to Earth. Okay,
Would
but
it still catch fire if it fell to the Earth?
when objects fall through Earth's atmosphere because they lost their orbit, or they
fall apart.
they kind of fall apart. Yeah, actually that's a good point. It kind of goes against, well, I was going to say it goes against, was it Gravity, the movie Gravity, where she re-entered Earth's atmosphere? But definitely when our people, Apollo missions and like that, they returned in a capsule. So you can, if you have heat shields, come back through Earth's atmosphere. But, I don't know. It's interesting. So something orbiting is actually just kind of free falling. It's just kind of missing the Earth, okay, as it free falls. So if you go back to the International Space Station with those people floating around, okay, it's not that gravity isn't acting on them. It's just that basically as the International Space Station moves and they have a certain momentum or inertia, okay, they are falling, but it's free falling. They continue to fall. That's what makes them weightless. Okay, so there are a lot of things in the universe that must be conserved. Okay, and our universe only works if these things are always here. Okay, you can track them. So for instance, matter is conserved, energy is conserved, momentum is conserved, the linear momentum I talked about. Now, actually, something has a certain amount of momentum if it has a mass and it's moving. Okay, an object can stop, right? But that momentum is going to be transferred to something else. Okay? There's another type of momentum associated with an object that's moving in a circle, and it's called angular momentum. So it could be, this says it could be something like orbiting a planet, okay? Or it could be something spinning on its axis that has what we call angular momentum. So, thou shalt not, and actually, you can take matter and convert it to energy, and you can take energy and convert it to matter, but the math needs to work out. So here enters something about angular momentum that actually is going to be very important in, let's see, this is chapter 4, chapter 5, chapter 6. When we talk about the formation of our solar system, okay, the sun and the planets, this idea of conservation of angular momentum is important. So angular momentum is m is mass times v is velocity. And since it's going like this, r is actually the radius. So any movement like that, you find the center of the movement and out to the where the movement is, that's the r term, the radius. Okay. So angular momentum needs to be conserved. Okay, and actually that's why the angular momentum that the Earth had as it was created in our solar system, that it's kept it. If you've ever heard where spacecraft like, oh my gosh, I'm drawing a blank. What was the one? New Horizons. Spacecraft that actually go out there. New Horizons is the one that visited Pluto recently. So it gets a gravitational assist oftentimes from a planet, and it, not much, but it actually robs a little bit of this momentum. I've heard them talking about it. It robs a little bit of the momentum of the planet that it gets a boost around. No worries, but it's true. Okay, so this actually might kind of look like Kepler's first law. Kepler's first law, where we have the sun and the shape of the orbits of the planets are ellipses. Okay, going counterclockwise. So one of the things we said is that we would call this over here, we could call that perihelion. Does that make sense? This is perihelion and this is aphelion. Okay, so if r is small, find r up here. If r is small, okay, notice that if angular momentum stays the same, mass can't change of the planet, but the velocity can. So if r is small, velocity is great. That's kind of what we're talking about here. We said planets move fastest when they're at perihelion. Okay, and that was what Kepler's, I'm getting mixed up, second law, equal areas. Okay. And then out here at aphelion, okay, it's got a big R, V is less. Angular momentum is conserved. It's like a math game. Well, here's one for you. If a skater begins her little, whatever you call that, swirling thing, okay, on the ice, what happens if she draws her arms in?
Should move faster.
She moves faster, exactly. And that goes right along with whatever angular momentum she set in motion when she did her cool thing to twist off, okay? That's conserved. So she's making R smaller, so V needs to go up, okay? Velocity will increase. So that's conservation of angular momentum in a nutshell. Okay, so types of energy. Well, energy we can kind of think of, well, first off, energy cannot be created or destroyed. Actually, it can be created from matter in nuclear reaction. I have a slide coming up on that. Units of energy are joules in the metric system, or calories in the English system. You may have run into these terms, and actually in astronomy I do kind of want to talk a little bit about kinetic energy versus potential energy. Okay, potential energy is like what we call stored energy. Kinetic energy is energy that's being spent, oftentimes associated with motion, kinetic energy. Another type of energy, now this is more of a type than kind of the kinetic energy or potential energy. But over here you see kind of an assortment of types of energy. Stars give us radiation. Stars give us light. Light is one type of radiation. Okay, so radiative energy is one type of energy. Other types of energy, we can burn fuel. Actually, that's a chemical energy. We can have mechanical energy, okay, created as you ride your bike. All right. So with regard to kinetic energy, so kinetic energy is kind of the opposite of potential energy. Kinetic energy is energy doing its thing, caught in motion, oftentimes associated with motion. So one of the things we kind of need to be able to talk about is the temperature of stars. Okay, the temperature of stars. So how hot or how cold something is actually an indication of, on a small scale, how fast the atoms are moving. I know it seems kind of strange, but I almost need you to kind of switch gears from the stars to basically being able to look at atoms. Okay, little tiny atoms. How fast are they going? That's an indication. We can put our thermometer there and get a sense for how fast they're going. Okay. So these little particles, they're gas particles. Gas particles are great. They don't care what their neighbor is. They just bounce around. They fill their containers. So here we have a couple of chunks of gases, okay? And it's kind of like the vector thing we said. The longer the arrow of velocity, the faster it's going. So look over here, and if we call this A, from left to right, A to B, can you see where the B molecules are going a lot faster? Okay? So these are going slower. This is a lower temperature. This is a higher temperature. So that's kind of how that goes. But if you wanted to, so that's temperature. That's temperature. You use a thermometer to measure temperature. But if you wanted to look at an object and say that object has this much thermal energy, not only would it be a temperature, like how fast they're going, but also how dense that stuff is packed in there. So for instance, here we have a couple of scenarios. Actually, this looks like liquid water right at the boiling point temperature. Okay, water boils Fahrenheit, 212 Fahrenheit, 100 Celsius. So those water molecules are really going pretty darn fast. And they're packed in there, because one thing's about liquid is that it packs a lot better, liquid molecules, okay? When they're gaseous state, man, they're out of here if you don't contain them, okay? So there's that, and in here we have an oven, right, that is jacked up to 200 Celsius. So 100 Celsius, 200 Celsius. Now notice with regard to, these would be water vapor particles, water vapor molecules. So they have a longer arrow, they're going faster the higher temperature. So when we come to like say, well, how much thermal energy does this pan of water have, or how much thermal energy does this gas in that oven have, we have to not only consider how fast the molecules are moving, but how many there are. Case in point, there's a lot more, it's almost like a momentum thing. There's a lot more particles over here, it's denser, okay? So the water in the pot contains more thermal energy, someone did their math, I don't know what, more thermal energy because it's densely packed. Even though they're moving a little bit slower, okay, there's more of that. Yeah, it's kind of like a momentum thing, okay? Less thermal energy, more thermal energy. Higher temperature, lower temperature. So it's not just about temperature, it's about density. Or actually kind of ultimately mass of the object that objects that you're comparing. So temperature scale, so that I showed you Celsius and Fahrenheit, right? There's a third temperature scale that actually we're going to use in astronomy. Some of you guys know it's the Kelvin scale. So here we have the three temperature scales. Okay, we have the Kelvin scale, the Celsius scale, and the Fahrenheit scale. The Kelvin scale, Celsius scale, and the Fahrenheit scale. So with regard to water, we have some important places here. Water boils at, like we said a minute ago, 100 Celsius, 212 Fahrenheit. On the Kelvin scale, water boils at 373.15 Kelvin. Okay? So Kelvin actually is kind of a cooler, no pun intended. It's kind of a nicer, sweeter, awesomer sort of temperature scale. And the reason is this, what I just put up. The fact that on the Kelvin scale, we have something called absolute zero. So one of the things about matter is, it's funny how you say something always has to do this, something, everything's conserved. Well, all matter is in motion. So the little particles in everything, the little atoms, molecules, and everything have motion to them. Again, you put a thermometer there and you get a sense for how fast they're moving. Okay, everything is in motion, by definition. So here's the deal, though: the cooler an object becomes, the molecules and atoms move more slowly. Okay, so you would think, well, you can get cool to a temperature that they don't move anymore. And you're right. Okay, actually, graphically, that point is absolute zero. Zero on the Kelvin scale. Okay, so that's why the Kelvin scale is so important, is absolute zero. Okay, stop moving. Like, see, I think I got this right. So like Pluto, right? It's like the sun's here, and Pluto is basically beginning what we call the Kuiper belt, okay? So it's very cold out in Pluto. Pluto is about, I want to say, 5 to 12 Kelvin. Different zones of Pluto have different temperatures depending upon how close it is to the sun, too. While I'm thinking about it, oh my gosh, we went to Chicago. We took the train to Chicago, my husband and I, and we went to the planetarium in Chicago, great planetarium. But the little plaque for Pluto, okay, how does this say? It said, how cold, I know, it didn't say get this cold, but basically it showed a thermometer, and on the thermometer it showed like negative 300 Kelvin. That just threw me through the roof. In fact, I'm thinking about trying to get a hold of Neil deGrasse Tyson and tell him how terrible that is. So basically what they did at the Adler Planetarium is they have like a negative, is it going to work? negative, it's not gonna, negative 300 degrees Celsius. Negative 300 degrees Celsius. Like, dude, that is like, that temperature never exists. Because you can't get any colder than negative 273 Celsius. That's like negative Kelvin. You can't get negative Kelvin. But they have it on all their planets. So I know. So anyway. Why don't we take a break? It's a good place to take a break and come back at the bottom of the hour. And that will be good.